We're going to go ahead and get started, but I'm telling everybody to go ahead and chat me your first and last name, and we'll get started. When we last met, I was talking about chapter 9, and I worked several examples. And we still need to work some more examples specifically on conservation of momentum. But one I wanted to mention to you guys is, for instance, a nice little problem. Let me see if that was in the previous section. I pulled it up a second ago. There's this wonderful little conceptual problem that the book asks for. It's about a child and a sled. Let me see if, oh, here it is. Okay. Well, wait a second. Is that it? Yeah. Falling on or off a sled. It says an empty sled sliding on frictionless ice when Jeannie drops vertically from a tree down onto the sled. When she lands, does the sled speed up, slow down, or keep the same speed? Anybody have an idea what that answer is from what we've covered so far? You actually have enough from what I covered last time to understand, but it's not a it's not a bad mark if you don't know. You're still in the learning process, and chapter 9 is not on the test. So anybody? Someone says speed up. There is a. It all depends, really, to be honest with you. But in this case, the way they worded it, you're imagining the actual child coming straight down from the tree. You're seeing the sled sliding by, so you can sort of think of the sled as if it has a velocity only in the x direction, say, or only in the y direction, or even in a combination of the x and y direction, but nothing in the z. And then this person falls down from a tree with a velocity only in the z direction. So it's not contributing to the velocity that might be in the x direction. It's not contributing to the velocity that might be in the y direction. And it's not contributing to the velocity that could have both an x and y component at all. So basically, you're taking something that has no momentum but has a significant weight compared to a sled, uh, and combining it with something that's just the weight of a sled moving at a certain speed. And because of that, the total momentum must be conserved because you're treating the system as the child that's falling from the limb as well as the sled. So the force that the child puts on the sled is an internal force and not one that matters to the second law of thermodynamics at all. So what that means is the net external force on the system is zero because, yes, there was gravity acting on the child and there's gravity acting on the sled, but there's a normal force acting on the sled that exactly cancels out the weight of the sled, and there's a normal force that the sled is providing when Jeannie falls on the sled, and that too cancels out the force, not only the force of gravity, but the changing of momentum vertically that has to happen because when the person's falling, they're speeding up, speeding up, speeding up, and they reach their max speed just before hitting the sled. At that point, the sled not only has to hold them up, meaning supply a force equal to or greater than mg, but it also has to go greater than mg because you've got to accelerate the genie from whatever speed she has to zero. But the main thing to understand is that all those forces cancel each other out. There's no net force acting on the system. The only possible net force that might act on the system would be friction on the sled, but that's kind of why we solve a lot of sled problems because they're usually on ice and friction could be negligible. So, with that in mind, the net force on the system is zero, and that means the momentum is conserved. And since the momentum is conserved, that means the initial momentum before the collision is just the little mass m times the velocity that the sled has. After the after Genie falls onto the sled, the momentum is big M, the mass of Genie, plus little m, the mass of the sled, in parentheses, times this new velocity. But that has to be equal to the little mass times the velocity that the sled had because of conservation of momentum. And therefore, what we now have to do is take that little m times v and distribute that over big M times v plus little m times v, and therefore it will actually slow down. Okay. The reason why I allowed or told whoever says speed up, If Jeannie actually fell in such a way that maybe she didn't fall straight down, maybe she jumped off the limb just a little bit and happened to jump in the same direction as the sled was traveling, or even just a component of her velocity was parallel to the sled's velocity, then that little contribution would actually add to the sled, and that could cause it to speed up. Other than that, it's generally going to slow down just because you have to basically take the same m times v that you had for just the sled, and now that has to apply for the sled, which is going to have a momentum little m times this new velocity plus the big M times this new velocity, and those two have to add up to give you the same quantity you had before, so it has to slow down. Now, the follow up question, part two, it says later, Jeannie falls sideways off the sled. When she drops off, does the sled speed up, slow down, or keep the same speed? So they're talking about her falling off sideways. So if the sled's going this way, that means she sort of boom, fell over this way, or boom, fell over this way, not fell over this way or fell over this way. Anybody have an idea of whether that would cause the sled to speed up or slow down, or neither? Same speed. Very good. Yes. Now, if she did fall off backwards, there's some probability that she's going to push the sled faster a little bit. And if she fell off forward, there's a probability that she'd slow the sled down, and then she'd really slow it down because if she fell forward, the sled's going to run into her. But yes, you're exactly right. If she falls sideways, that should cause it to have the same speed. So that was just a good conceptual question that your book had, and I wanted to make sure everybody was up to speed on that and could answer that one. So let's get back to our other problems. There is a problem that I think is pretty interesting. Let's start with this. I'm going to say example one, and what we're going to do is we want to estimate the average force delivered by a karate chop. So estimate the average force delivered. Oh, I put the dot on part of my V instead of part of my I. There you go. Delivered to a board when a quotation mark, whoa, Nelly, karate chop breaks.
You share your screen too when you have a moment.
Yeah, I will. Thank you. I'm glad you reminded me because I would have forgot again. Okay. So when the karate chop breaks a board, assume the hand is initially moving at 10 meters per second. Okay, so yes, absolutely. You guys need to see the iPad for this one. So I'm going to go ahead and share the screen with you. It should pop up in a second. I've just got the wording for the problem written out. Haven't really made any estimates or anything. But a typical board you can imagine is obviously somewhere less than maybe 1 inch, but definitely a little bit less than 1 inch. So I'm going to go on the assumption that it's 2 centimeters thick. So I'm going to make the assumption that because they're asking us to estimate, by the way, I'm going to go on the assumption that I'm watching a person demonstrate a karate chop that breaks a board in half, and I'm going to assume that the thickness of the board is going to be 2 centimeters. So under my solution, assume uh, delta x equals the board thickness is about 2.00 centimeters, and the mass of the human hand. Now, there actually are uh, areas where you can go and find exactly these figures out. So, specifically in kinesiology or in the field of sports science, this is partly what they study. So, we've, for instance, taken cadaver parts and weighed, the individual hand, weighed the lower part of a leg, weigh the upper part of a leg, weigh the torso, weigh the upper part of the arm, weigh the lower part of the arm, find the center of mass of the lower part of the leg, find the center of mass of the upper part of the leg, all that kind of stuff. What's the weight of the head? You might remember, I think Jonathan Lipnicki was his name, the little kid on Jerry Maguire. He said the human head weighs 13 pounds. Okay, there's literally tables of this stuff where it not only can give you the weight, as what they normally do is they'll say some percentage of the total weight. So if you assume the human weighs 200 pounds, they'll give you a percentage, and you multiply that percentage to 200 pounds, and that'll give you the mass of, say, the lower leg. And they'll give you a percentage of the length of the lower leg or a percentage of the height. Uh, of the person is the center of mass of the human leg or whatever, and from that you can tell all sorts of things, and treat the body as if it's an assembly of parts. So what I'm going to do is I'm going to use something like that idea, and I'm going on the assumption that the human hand is about 1 kilogram, and by doing this, I should be able to use basically our kinematic equations and our understanding of physics to estimate roughly the force required to break a 2 centimeter thick board. So, what we're going to imagine is that there's a hand. Uh, so, there's a hand coming downward with a velocity of 10.0 meters per second. It's going to strike a board whose thickness, delta x, is equal to 2.00 centimeters. And I'm going to imagine, in fact, that this means the this means that the hand will go from 10 meters per second to 0 meters per second. So v hand is equal to 0. V hand initial is equal to 10.0 meters per second. And we can use something like that. So, what we do know also is the summation of the forces is equal to dp dt. And again, this is a vector equation, but we're only dealing with one dimension, so we can make it a little simpler by just thinking about it going in the up down direction, which might be the z direction, might be the y direction. Doesn't really matter too bad, long as you have some idea of what it is. You can say the summation of the forces in the y direction equals dpy over dt, and that works fine. What we want to get, though, is the average force. So if we manipulate this equation in such a way that we can come up with a equation for impulse, then we could possibly figure it out. So what I'm going to do is multiply both sides of the equation by dt, and that's going to give me the summation of the forces in the y direction dt is equal to dp. Now, in principle, that means we'd probably integrate that, and that would work fine. But if we just want to think about it, we could say on average, the f, put a bar over it. That's one way of saying average. Another way of saying average would be put it in greater than, and later and less than brackets. That's another way of calling an average. We can say that that average can be related. So we'll say the summation of the sum of all the forces times delta T is approximately equal to delta P sub Y. Again, everything's sub Y here, so that's okay. So if we figure out some way to find out the change in momentum and the time that the hand would be in contact, then we could work out and find out exactly what the average force, summation of force in the Y direction. Now, I'm putting the summation of forces in the Y direction not because I'm going to add a bunch of different forces, but just remind you that Newton's second law is not about a single particular force. It's about all the forces acting on the object. In this case, the biggest force acting on the board is the hand. So that's just going to turn out to be the force due to the hand. So if we look at it that way, we could say, okay, well, I need to know what is the change in momentum. Well, the change in momentum in the y direction would be mass times velocity final in the y direction minus mass times velocity initial in the y direction. And you can see that this is going to be roughly 1.00 kilogram. That's the mass of the hand. And of course, that's the same mass for both parts. But you can see that the final velocity, if I allow the hand to go completely through the thickness of the board, the final velocity will be reaching zero at the bottom of the board. So I'm going to say zero point 0.0 meters per second minus 10.0 meters per second. And you can see automatically that this gives us a delta P that's in the negative direction. And that's because we've chosen P, the direction the object's initially going, which was down. We've chosen that to be the positive direction. And obviously, it's got to absorb a force in the negative direction, upwards, in other words, to bring it to a stop. Obviously, 10 times 1 is just 10.0 kilograms, meters per second, and of course the negatives there. We are only going to care about the magnitude though, so I'll be ditching that. And that's something you do all the time. So uh, a lot of times you just need to compare magnitudes. Uh, there are specific ways where you can always keep the signs and that sort of stuff, but sometimes that takes more equations to put together and other principles to put together. Whereas you just know physically from experience that, hey, if two forces are acting on an object and we want to find the situation when the acceleration is zero, that's when those two forces are equal to each other. So instead of saying the summation of forces is equal to mass times acceleration and then plugging in A equals zero and then solving it, you could just say F1 equals F2. That's sort of what I'm doing here. So now I got that change in momentum. Now I need to figure out is how much time it's going to take for the hand to go from 10 meters per second downward to 0 meters per second. So there's some kinematic equations you could use. For instance, you could use, in this case, since we're talking about y, you might be compelled to write it as a y equation, but remember I did introduce it as an x, so I'll just say it this way. 1/2 at squared plus v0t plus x0. That's one way. And in order to do that, we'd have to have some idea what the acceleration is. We know what the initial velocity is, and we would find out what the initial position, which we could just set to zero, and we set the final position to 10 centimeters plus, or excuse me, 2 centimeters plus zero. That works, but it's not necessarily the best way. We also had this equation, v squared is equal to v0 squared plus 2a x minus x0. That could work. We could call the x minus x0 the actual delta x, what we're talking about, but that doesn't really allow us for time, and we're trying to solve for the time, so it's not that helpful. But what we can do is there's another equation that came from uh, assuming that the acceleration is constant. And that was one that we don't use that often, but I do tell it to people. And that is the average velocity is just 1/2 of v0 plus v1 All three of these equations are only true when the acceleration is equal to a constant. So we're going to make the assumption that the acceleration is a constant, or at a bare minimum, we're at least working with the average acceleration, so these equations would still work. So if I realize that distance, if you look at, for instance, x equals 1 half at squared plus v0t, if you were looking at it as if it had no acceleration, you could just say x is equal to v0t, and that would work fine. But what we're going to do here is we're going to, I think I'll do it that way. Yeah. So I'm going to take the average velocity as 1/2 of the initial velocity plus the final velocity. And the initial velocity, of course, is 10 meters per second. The final velocity is 0. So 1/2 of 10 plus 0 is 1/2 of 10, which is 5 meters per second. So we can actually say that the average velocity is 5 meters per second. So I'm saying equals 1/2 0.0 meters per second. All right, let's call that one a 10 plus 0.0 meters per second. That's where that actually came from. So we could do that, and then we could just say x, the distance traveled, is equal to the average velocity times time. We know that's true. That's one of the fundamental equations that we use. In fact, it came from the definition of average velocity. Average velocity is x final minus x initial over t final minus t initial. So this equation works perfectly for that. And therefore, we can say delta t, which is what we chose to call the time, is going to be the same thing as time in that equation I just wrote. So I'm going to say delta t is actually equal to delta x, which is what we called the thickness of the board, divided by v bar. So delta t is going to equal 5.00 meters per second. Oops, excuse me, put it in the wrong slot. Watch out for that. Delta x is 2.00 times 10 to the negative 2 centimeters, or excuse me, meters. And then I'm going to divide that by 5.00 meters per second. And when you do that, you can see not too bad. You can do it on your own without the calculator even. So 2 10 to the negative 2 divided by 5 gives me 0.004 seconds. So that's actually how long it will take for the hand to traverse the thickness of the board. Now that we have that, we can say uh, F bar times delta T is equal to delta P. So F bar or F average is just delta P over delta T, which is, we already calculated the delta P. Again, I only care about the magnitude, so I'm going to say 10.0 kilograms meters per second divided by 0.00400 seconds. That's 4 over tenths, hundredths, thousands. That's 4 over 1,000. So, 0.004 being 4 over 1,000 means that we're basically multiplying 10 times 1,000 and then dividing it by 4. So that gives us 10,000. That means the answer is 2,500 newtons. So that's roughly what the force on average would be. F is about 2,500 newtons, carrying an extra digit that's not significant, of course. And I could tell you that that is about 2.242. So I'm going to divide 2,500 divided by 2. I think it's 2.224, 242. Maybe that's it. I can't remember. Anyways, I'll do that, and that's on the order of 1,100 pounds. So that gives you a good idea of roughly the size of the force that hand applies to the board in this particular situation. Anybody have any questions on that one? So there was no really. I mean, there's wrong ways to do it, of course, but you could have used x equals 1/2 at squared. You just have to figure out some way to come up with the acceleration. Uh, I chose to ignore trying to find the acceleration and just use the average velocity. And then whenever you use the average velocity, you always know that the distance traveled is the average velocity times the time taken. So that's just the way I chose to do it. You don't have to choose to do it that way. In fact, you could just say v squared is equal to v0 squared plus 2a times delta x. We know delta x, we know v squared, we know v0 squared, and we just solve for a, and then we could use the a to figure out the time required for delta x. So you could use the a from the v squared equation, put that in the x equals 1/2 at squared equation, and solve for t, and that would actually get it as well. Any of those ways are perfectly fine. Any of those kinematic tricks that you use would be fine. I don't see a real way we could easily use conservation of energy to calculate the force. In fact, forces and vector quantities are usually the difficult thing to get out of a conservation of energy problem. That's sort of the whole purpose of the paradigm of using conservation of energy and those types of laws, because they are non-vectorial. And if you want something that's vectorial, you almost always just be as efficient to use Newton's second law and solve for it than you would be using energy and then trying to work it backwards to find out what the vector quantity is. So, any questions on that? All right. So that's a pretty good little impulse related equation. You'll notice that F times delta T, which for some period of time when we were looking over here, uh, that F times delta T, which is also equal to delta P, both of those are equal to the impulse. So we are, in some sense, using impulse, but the main thing is, I just want to point that out that we're using impulse again. Let's move on now to a little bit more about conservation of energy. And in order to do that, I need to give you a little bit of an idea of what it means to say momentum is conserved, and then for an elastic collision, what does it mean to say that kinetic energy is conserved? So we're going to start off in the simplest case, and specifically, we're going to talk about collisions that are really one-dimensional, meaning you can imagine wires are a straight wire with beads on it, and you slinging them back and forth towards each other. That's a sort of one-dimensional conservation of momentum problem. But you could also think, as long as you're making sure all your hits are head on, then you could also think about pull balls. So when you shoot a cue ball towards a nine ball or something like that, unless you hit it a little off axis, which is going to cause, the nine ball to go at one angle and the cue ball to go at another angle, uh, if you didn't do that, then the nine ball could be hit by the cue ball and go straight in the same direction parallel to what the cue ball was. And that would then be a one dimensional problem. So that's what we're looking at. So the way I'm going to voice it initially, or picture it initially, is we're going to imagine that there's an object. I should probably write in something other than laser pointer. So we're going to imagine a point particle or something like that. This object has a mass m sub a, and it would be moving, for instance, with a velocity v sub a. And then this mass over here would have a mass m sub b, and it could be moving with a velocity v sub b. Now, when I was taking this course and the algebra-based physics course before it, I would often call VA a positive quantity, but then I'd stick the negative sign in front of VB because it's clearly pointing the other way. I've learned that it's a little bit cleaner if I just keep everything positives, and then the negative signs will come out from the math. So that's what we're doing here. We're going to imagine that this is one photo we look at, And then if we look a split second later, we're going to find that MA and MB are right next to each other and a collision has occurred. And then if we look at another slide a second later, what we're going to discover is MA is now moving, let's say this way, with a velocity VA prime, and MB is moving this way with a velocity VB prime. And they're still vector quantities. Just remember, in one dimension, vector quantity has its characteristic direction indicated by either a positive sign or a negative sign. So if I chose, for instance, to say that the positive direction is to the right, then if I solve for VA or VB prime, both of those would come out positive. Whereas if I solve for VB or VA prime, both of those would come out negative. So that's just the way we're going to work it. Now, taking conservation of energy. So if we assume momentum is conserved. Anybody can anybody tell me what condition must be happening for momentum to be conserved? This is a big concept that anybody that finishes a course in physics should be able to answer. You guys haven't finished it yet, but you might have got it already from the reading. So, can anybody tell me what condition is necessary for momentum to be conserved? The net external force on the system is zero. That's the absolute necessary condition. But if it's really close to zero, we often will use that at least as a first order approximation to the answer. So that's what it is. Remember, it comes from the fact that the summation of the forces is equal to dp dt. And if the summation forces is equal to zero, then dp dt is equal to zero. And of course, that implies p is equal to a constant. That's the fact that says, hey, momentum is conserved. P equals a constant. That means momentum is conserved. So, with that in mind, what we're going to do is say MA VA plus MB VB. This is P initial. Okay. And again, I'm sort of leaving off the vector symbols because, again, it's one dimensional. So ultimately, we'll get some of them are positive and some of them are negatives. And the positives will indicate they're going in one direction, and the negatives will indicate they're going the opposite direction. And it really just depends on which you choose to be. So, what this tells us, the initial momentum being MAVA plus MBVB, that tells us that the system is mass MA and mass MB combined. So we're not using F equals MA or F equals dBdt for the mass A, nor are we using it for the mass B. We're using it for the system, which includes mass A and mass B. The final momentum, as drawn by the diagram, is going to be MAVA prime plus MBVB prime. So conservation demands that MAVA plus MBVB is equal to MA VA prime plus MB VB prime. So this is very important. This is the equation for a one-dimensional collision in which momentum is conserved. Now I've got to introduce the other equation. If the collision is elastic, then kinetic energy of the system is conserved. So what does that mean? That means the kinetic energy initial is equal to 1 half ma va squared plus 1 half mb vb squared. The kinetic energy final, which remember this is a scalar quantity, that's how you have the v squareds here. This is going to be 1 half MAVA prime squared plus 1 half MB VB prime squared. And then conservation would dictate that we get 1 half MAVA squared plus 1 half MB VB squared is equal to 1 half MA VA prime squared plus 1 half MB VB prime squared. And that's our other equation. Okay. So I'll just call this equation one and I'll call this equation two. So that's what conservation of kinetic energy and conservation of momentum mean. And it doesn't just have to be a head-on collision this way. It could be a head-on collision where this one's going a little bit slower than this one, so this guy rams in the rear end. And that would just be a case where the initial velocities of both objects is both have the same sign. Normally, you'd say it's moving to the right, and we'd call it positive, but you're allowed to choose any direction positive. So I just say they're both going with the same, or they both have the same sign when they're traveling like this, right? If they were traveling like this, then one has to have one sign and the other one's got to have the opposite. And then after the collision, they could bump in such a way that one of them goes backwards and the other one goes that way. That means they have the different signs from each one. But it's pretty straightforward to do this. The nice way of looking at this is we're going to get all the A velocities on one side. So to solve this one and two equation system, use one to get all of the VAs on one side and the VBs on the other. Okay. So what do I mean by that? I'm going to take equation one and I'm going to subtract MAVA prime from both sides. And I'm then going to subtract MBVB from both sides. So I'll say MAVA plus MBVB minus MAVA prime minus MBVB. is equal to, now the other side was originally MAVA prime plus MB VB prime, but I just subtracted MAVA prime from both sides, and I just subtracted MB prime from both sides. Or excuse me, not VB prime, just plain VB. So the reason I'm showing you all that is you now see that the MB VB is going to cancel out with the MB VB, and you're going to see on the other side the MA VA is going to cancel out with the minus MA VA, and in fact, our result will be MA times VA minus VA prime is equal to MB times VB prime minus VB. So we now have what I would call equation 1A, say. Okay. Now that's kind of helpful. It's not really where we're going, but now I'm going to do the same thing. Now we do the same thing to, oops, equation 2. So again, I'll write down 1/2 MA VA squared plus 1/2 MB VB squared. I'm going to leave a space and say equals 1/2 MA VA prime squared plus 1/2 MB VB prime squared. What I'm going to do right now is multiply both sides by 2, and that'll get rid of the 1/2. And then I'm also going to uh, do like I said before. I'm going to get all the VAs on one side and all the VBs on the other side. So I'm going to subtract MB VB squared, and I'm going to subtract MA VA prime squared. This was MB VB squared, not prime. And I'm going to do the same thing over here. I have to subtract MA VA prime squared, and I have to subtract MB VB squared. Okay. Now that I've done that, you can see that the MB VB squared cancels out with the MB VB squared, and the MA VA prime squared cancels out with the MA VA prime squared there, and I am left with MA VA squared minus VA prime squared is equal to MB VB squared, excuse me, VB prime squared minus VB squared, like that. I'm going to call this equation, actually, did I call it II or did I call it 2? I did call it 2, so excuse me about that. This will be equation 2A. Okay. Now, these look crazy, but let's put them next to each other and then I'll tell you the next step. So if I put whoa, might help if I use again the writing marker. MA VA squared minus VA prime squared. And actually, it probably help if I wrote my exponent a little higher. So that is equal to MB. Oop, there's a minus in here too. VB prime squared minus VB squared like that. Now, if I put under that MA VA minus VA prime equals MB VB prime minus VB, you don't necessarily see anything particularly helpful until I do this. And you got to remember from grade school now, what is VA squared minus VA prime squared? Anybody remember how to factor that? Okay, so now you can see that first off, does everybody recognize how I did that combination there where I made the three factors on the left out of the just two factors and then the three factors on the right out of just two factors? Everybody see how I did that? Anybody have any, excuse me, anybody have any questions on that? All right. Well, it looks like we don't, so that's a good thing. What we're now going to do is I'm just going to divide 2b by 1a. Okay. You can see what happens when I divide. Basically, what we're going to get is the MA and the MB is going to cancel out, and the minus one's going to cancel out. So all I'm left on the left-hand side with is VA plus VA prime, and all I'm left with on the right-hand side is VB plus VB prime plus VB. So what we have now is a new equation that in some sense is a combination of the first two. So we can use that in lieu of using one and two together, and then we could just use one with it, or we can use two with it, and that'll give us a lot of stuff. And in fact, the way we normally write it is we go VA minus VB. In other words, now I'm trying to get them before the collision on one side and after the collision on the other. And that's going to give us VB prime minus VA prime. So what you see is they sort of change orders. So another way you could write it is VA minus VB is equal to negative VA prime minus VB prime. So the subtraction more or less changes signs. That's a way of looking at it. And in fact, I'm going to call this equation 3, and this is one of the goals that we were going for. So now we have that particular equation that we can use in addition to equations 1 and 2. So let's now use that so we can see how we can go about solving problems. So let's go for example. This will be example 2. So what I'm going to do with example 2 is I'm going to imagine uh, basically pay and pull. So I'll just write it out. Pool ball A and B. So I'll say S. Pool balls A and B have the same mass M, and A is initially moving with velocity VA when it collides with B, which was at rest. So I'm going to go ahead and interpret that VB is equal to zero. Now, with that in mind, what I want to know is what are the speeds of the balls after collision? So what are V prime, VA prime, and VB prime? So that's the question. Solution. We know, for instance, that MA VA minus VA prime is equal to MB VB prime. Oops. Yes, VB prime minus VB is one equation. We also know that you can trade the orders, so it'd be VA minus VB is equal to negative VA prime minus VB prime. So there's two equations we could use, and we can go about solving it as follows. First off, we're taking VB is equal to zero. Therefore, we get, by the way, MA is equal to MB is just equal to M. So we can combine all this stuff to get M times VA minus VA prime is equal to MB VB prime. In other words, the VB has disappeared, and what we see is we have an equation VA prime, or we have an equation that includes M. Oops, that subscript's not supposed to be there. We're changing all the M's to just plain M instead of MB and MA. But this one has two unknowns. With that in mind, we're kind of in a little bit of a tight uh, crunch. So I'm going to use the other equation, which says that VA, oops, I erased a bunch of stuff by accident. The other equation, which says VA and VB is zero, so it's going to say VA is equal to negative VA prime minus VB prime, like that. Uh, Now we can combine these two. I'm going to call this equation A. I'm going to call this equation B. And we already know VA, but we can use equation B to solve for, let's say, VA prime and then plug that into B. So solve B for, I'm going to say VB prime and plug into A. Notice how I'm using my words to say what I've done, what I haven't done. What often happens when you're solving systems of equations, you'll accidentally not use one of the equations. And if you have two unknowns and you have two equations, you absolutely have to use both. If you have 12 unknowns, you have to have 12 equations. If you use less than 12 equations, then whatever answer you get is suspect at best. So this allows you to keep track of exactly what you used. But solving B for VB prime, all I will get is, notice if I distribute that negative, I'd get VA equals negative VA prime plus VB prime. So VB prime is just going to be VA plus VA prime. So this means VB prime is equal to VA plus VA prime. Now I'm going to plug that into equation A. So I'm going to say now M times VA minus M times VA prime is equal to M times VB prime. Now, at that point, you already see that all the masses can cancel out. So I could, for instance, multiply by 1 over M on this side and then do it again on that side. And that would be nice. And I'd get VA minus VA prime is equal to VB prime. But now I'm going to use what VB prime is. So I'm going to take this and plug it in there. That's going to give me VA minus VA prime is equal to VA plus VA prime. Now you can see what happens if I subtract VA from both sides. I'll say minus VA minus VA. And then what I get is obviously negative VA prime equals positive VA prime, which implies VA prime is equal to 0. So that means what you've probably seen before if you've ever played pool, there's a lot of times where you hit a cue ball and it goes up and hits in, let's say the two ball or the eight ball or something like that, and comes completely to a stop, and then the cue ball or the two ball, whichever one you hit, goes on moving. That's what we just discovered. So this is one answer. Now that I have that, I can plug that back into VB prime. So let's say plug this VA prime into our equation, oops, for VB prime. So plugging that in, our equation for VP prime is VB prime is equal to VA plus VA prime. And now we get VB prime is equal to VA plus 0. Therefore, VB prime is equal to VA. So that's actually the answer. This is not unlike Newton's cradle. You've probably seen Newton's cradle. I used to have one laying somewhere around here, but it's basically just a metal frame like this and another metal frame just like that. And it's got a string tied from the metal frame closest to me down to a ball, and then from that ball back up to the frame farthest from me, and then another one, another. So it has like 5 balls. If you lift up one ball and drop it, it swings down, hits the end of the 5 balls, and then the fifth ball on the very end takes off and reaches essentially the same height that the initial ball was lifted at. If you watch it over time, you realize it's a little bit less than the initial height, but the point is, in that case, if you did it with just 2 balls, it would be exactly this collision we're looking at. The only difference is we did it with 5 balls, so it just takes that momentum and carries it down from the first ball to the second to the third to the fourth to the fifth, and then the fifth kicks out. Okay, so that's what happens when one ball is sitting still and the other ball is moving. Now with example 3, we can do the same thing, only this time we're going to do it as if the both balls are moving. So let's look at example 3. Repeat the previous problem. Oops. Without assuming VB or VA is equal to 0. In other words, we're going to assume both of them are moving. We don't know necessarily anything about them moving. We know that they're moving, so we're going to try to find out what we get with that. Does that make sense to everyone? All right. So what I'm going to do again, we'll do solution. And for the solution, we're going to need our equation 3 that we discovered, which is the changing of the orders. So VA minus VB is equal to negative VA minus VA prime, that is minus VB prime, like that. We're also going to make use of conservation of momentum, which would be, since M is equal to M, we're actually going to get, or since MA is equal to MB is equal to M, we're going to get MVA plus MVB is equal to MVA prime plus MVB prime. But in fact, I can go ahead and divide through by all these masses, and I just have VA plus VB equals VA plus VB is equal to VA prime plus VB prime. Okay, so I'm going to call this equation A and I'm going to call this equation B, and we're going to figure out what we can do with them. So let's actually add the two equations. So add equation A and, and, uh, and equation. This will be my abbreviation for equation, by the way, EQN B. When I do that, I'm going to get VA minus VB plus VA plus VB is equal to, I'm going to go ahead and distribute the negative. This is negative VA prime plus VB prime. And this one's going to be equal to VA prime plus VB prime. So when I add the two, I get VA plus VA is 2VA, but VB minus VB is 0. And then on the right hand side, I get VA prime minus VA prime, and then I get 2VB prime. So this tells us that VB prime is actually equal to VA. So that's one of our answers. Now I'm going to subtract the equations. I think that'll work. So in this case, I'll say VA minus VB equals negative VA prime plus VB prime. And this time I'm going to say minus VA plus VB. Actually, I'll leave that parenthesis around the whole thing and say VA prime plus VB prime. Now, notice the minus goes across the whole thing. So now I'm getting VA minus VA on the left-hand side, but I'm getting negative VB minus VB. So this would be negative 2VB. On the right-hand side, I'm getting uh, negative VA prime plus negative VA prime gives me negative 2VA prime. And I'm also getting VB prime minus VB prime, so that's all. And in fact, this one gives me that VA prime is actually just equal to VB. So in this case, what happens is the particles collide and they just exchange velocities. So an example might be something like this. You have a black ball moving at 3.00 meters per second, and you have another ball that is, let's say, I'm going to Yeah, I think I'll take them both going like this. I'm going to say this is 1.00 meters per second. Then they're going to collide, and then they're going to go off. And this time, what's going to happen is this ball is now moving with a velocity of 1.00 meters per second, but this one is moving with a velocity of 3.00 meters per second. So that's what happened with that one. Anybody have any questions on that? Does that make sense? Okay, let's try another example. By the way, I should probably clarify what this one did too. Let's draw a little diagram like I just did. In this case, we have this ball, let's say, moving at 3.00 meters per second, and this ball was sitting still. Then we had these two collide. Then what we had was the black ball sitting still, but now the white ball is moving at 3.00 meters per second. So that's what happened with that one. If you imagine Newton's cradle again, like I mentioned a second ago, you can sort of see how that's related because you could imagine a string coming down to a ball. Now, this one I made a really big Newton's cradle. I did 9 balls instead of 5 or 7. Okay. If I lift this guy up to this height and then allow it to fall down, then this guy is going to pop up to this height when it hits. And that's just because when the red ball hit to the left, it came to a stop, just like the black ball did above. And if it was just 2 balls, you could see it immediately, but just trust me, it goes through all the balls. And then the white ball, which went off at 3 meters per second above, does the same thing here for the rightmost ball. So the rightmost ball, Newton's cradle, will actually leave with the same speed that the leftmost ball had. And therefore, since it's about the same speed, it should go about the same height before it comes to a stop. So that's what's going on with those two examples. Oops. Ooh, I ran out of paper. I didn't really, but I sort of did. Oh, did I start like wait? Oh yeah, no wonder. I started on like page 8. What the heck? I will move these in the proper order when I get before I post them. So if you look at them on my YouTube channel, they'll be right. So don't worry too much with that. Just know that that's kind of a goofy thing. So let's say this is example 4. So example 4. Uh, let's imagine this scenario. So we're going to have a ball. This one has a mass. Are we going to use the same masses here? No, we are not going to use the same masses here. So this one's going to be mass A, and it's going to be moving with a velocity. Oh man, I was looking so good too. It's going to be moving with a velocity VA towards this other one that's sitting still. This one's going to be mass B, but VB is equal to 0. Again, that's going to give us a collision. And then after the collision, what we're going to get is these balls moving at some new speeds. And what we'd like to know is assuming it's an elastic collision, head-on collision. And what we want to know is A, we want to know VA prime and we want to know VB prime. In terms of the initial, yeah, gotcha. And part B, we want to know VA prime equals and VB prime equals if MA is much, much greater than MB. So this is a potentially horrible situation where you're imagining like a Mack truck running into Cooper or a Cooper Mini or something like that. That's what part B is. And part C, we're going to do the same thing again, except we're going to reverse it. We're going to say what is VA prime, what is VB prime if MB is much, much greater than MA. So in this case, uh, you're imagining in this case the Mack truck is sitting still and it gets hit by the basically the Cooper Mini. So that's what we're working out. It is an elastic collision, so all those equations we found are fair game. I'm going to say solution, and what we know is MAVA plus MB VB is equal to MAVA prime plus MB VB prime. We also know that VA minus VB is equal to negative VA prime minus VB prime. Okay, so our job here is to try to figure out a way to actually solve for this. Now, what we do know also is VB is 0, and that's true here as well. So we can do a little bit of work with that. And what we're going to say now is we have MAVA is equal to MAVA prime plus MBVB prime. And we also have VA is equal to negative VA prime plus VB prime. So those are our two equations. We can try to use one for the other. For instance, let's solve this one, the right one. I'm going to solve that for VA prime. So VA prime is going to equal VB prime minus VA. And now I'm going to take this and plug it in there. In so doing, I'm going to get MAVA equals MA. Now in place of VA prime, I'm writing VB prime minus VA plus MB VB prime. Now I only have one unknown now. It's just VB prime. So I want to get all those terms on the same side, and I want to get all the other terms on the other side. I've got a negative MAVA on the right, so that's going to make 2 MAVA on the left. That takes care of this one and this one. And then I've got MAVA prime plus MBVB prime. MAVB prime. So, I shouldn't put a plus there. I should put it equals. So this is going to be MA plus MB times VB prime. and that gives me VB prime is equal to 2MA, and actually I'll leave that VA somewhere else, 2MA over MA plus MB. And hopefully this looks a little familiar to you because that helps you memorize the equation. This is just like the equation for the tension in the Atwood machine. It looks a lot like it. It's missing a little bit, but the main thing is that is the right answer. Now that we have that, we can figure out what the answer VA prime is. So VA prime we found was we found VA prime was equal to VB prime minus VA. I just figured out what VB prime is, so I'm going to write VA prime is equal to 2MA over MA plus MB times VA minus VA. Now that means I need a common denominator. So I'm going to write the numerator for the left fraction as 2MA. The numerator for the right fraction is negative MA, negative MB. And then, of course, the denominator is MA plus MB. And we see that we have a common factor of VA out in front or out to the side. So now we can see that 2MA minus MA is going to cancel each other out and just leave MA minus MB. So not only did that last one look like the Atwood machine, this one looks even more like the Atwood machine because this one's the one for the not for the tension, but for the acceleration. It was the difference divided by the sum. So here, darn it. So here, what we get is MA minus MB over MA plus MB. All of that times VA, and that is our answer. Now, far as part B and C go, I can do that kind of quickly. For part B, that's when we're saying MA is much, much greater than MB. With MA much greater than MB, then you can see the denominator here is just going to become MA. And then the MA over the MA is going to cancel out, and you get a really horrifying result that specifically VB prime is equal to 2VA as MA is much greater than MB. In other words, when the impacting object is like a Mack truck and this thing that's sitting still is like a Cooper Mini, then that means the Cooper Mini is going to take off at twice the velocity that the Mack truck had. So if the Mack truck runs into the tail end of a Cooper Mini at 60 miles per hour, it's not unreasonable to think that the Cooper Mini is going to leave at like 120 miles per hour. So yeah, it's really horrible. And not only that, you can find that VA prime is going to be, notice when you let MA be much greater than MB, then this one and this one just leaves MA. This one and this one just leaves MA. So you get VA is approximately equal, or VA prime is approximately equal to VA. So the Mack truck's hardly going to notice it's what we're saying there. I'll leave the other one up to you guys. I'll actually finish it here, but you guys might need to leave. Time is up. You're welcome to stick around if you have any questions. I'm going to wait for the last person to leave. Make sure you chatted me your first and last name if you hadn't already. And everybody, don't forget to get your tests done. You got an online test and a face-to-face test through Chapter 8. It does not include Chapter 9. I might make you another practice test since I discovered it's got Chapter 9 in it. I apologize for that. If I do, I'll send you an email, let you know. But I'm going to go ahead and do Part C here when you guys go and at least write the answers out and explain it. But you guys are free to go. Thanks for coming. Zach, did you have any questions? All right. For Part C, again, I'm doing this because it's just a couple minutes. We wasted a little bit of time at the beginning, so I want to go ahead and finish Part C. If you look at Part C, we're supposed to take these same two equations that I got boxed off in red, but in this case, we're trying to consider the case of MB being much, much, much greater than MA. If MB is much, much greater than MA, then what's going to happen is this MB is on the numerator is essentially just going to be negative MB. And this MB plus MA is essentially just going to be MB. So these MAs are negligible, and you end up getting negative MB over positive MB times VA. So what that tells us, and that was supposed to be VA prime. I didn't mark it correctly. Hopefully my students caught that. But that was VA prime. Now, for part C, what we just found was VA prime is actually equal to negative VA. So this means, for instance, that a Cooper Mini runs into the tail end of a Mack truck because the Mack truck's so much heavier than the Cooper Mini. The Cooper Mini is basically going to hit it and fly backwards at the exact same speed that it had. That's more or less what VA equals negative VA prime or negative VA equals. Now, the other case is VB prime. And in that case, we're going to say MB is much, much greater than MA. So MB being much, much greater than MA means this part right here, MA plus MB, is just roughly MB. And then MB under MA is essentially zero. So VB is essentially going to be zero. VB prime is essentially going to be zero. And this is if MB is much, much greater than MA. So that's the answer to part C, and we've now completed this one as well. I hope that helps everyone, and thank you everybody for coming. I'm going to go ahead and stop sharing and call it a day. Thanks again, everybody. Bye bye.